Okay, good morning. Welcome to session 8 of Rose's 2021. I think we'll wait maybe 1 or 2 minutes to go ahead and get started. But before we begin, I do want to acknowledge that Rose's 2021 is supported by a number of organizations with both financially and in-kind support. So we'd like to acknowledge the Seismological Society of America, the seismology section of the American Geophysical Union, the University of Alaska Satellite Facility, and IRIS, the Incorporated Research Institutions for Seismology, for all of their support for running our program this summer. So I think we may go ahead and get started. I'm very excited. Today we have Dr. Jelle Assink with us, who's going to be speaking about seismoacoustics. Dr. Assink got his PhD at the University of Mississippi here in the US. And then after that, he did a postdoc at CEA in France. And he is now a senior geophysicist at the Royal Netherlands Meteorological Institute, or KNMI. And he's going to be talking to us today about the intersection between seismology and acoustics and some of the research that he does in those topics. So I think with that, just a reminder that we have our Q&A, so feel free to ask questions in either the Q&A and I will verbalize them to him throughout the presentation. I think with that, we can go ahead and get started.
Hey, great. Thanks, Francisca, for this nice introduction. Yes, I do work for the Dutch King, the Royal Netherlands Meteorological Institute. We are a meteorological institute, but we also do a lot of seismology and acoustics. So we are nicely in between meteorology and seismology. So today I would like to do a few things together with you all. First, I will give a short lecture. Or at least I hope it's going to be short. Otherwise, Francisca, please stop me. And then I have prepared a Jupyter notebook with a tutorial how to process seismoacoustic data, and I would like to go with you through it. So without further ado, I would like to share my screen and start the presentation. Okay. Oops. Okay, so yeah, the topic of today is seismoacoustics, or as I say, the Earth as a loudspeaker, and what can we learn from its sounds. And as we will see today, we can learn a lot from it. Seismoacoustics is a topic that we at KNMI have been studying a lot over the past few years. Not just me, but also my colleagues in our group that are at KNMI, but also at the Delft University of Technology. So today I will also show work that we have done in collaboration with my colleagues, Gil Averbuch, who is currently at SMU in Dallas, Texas, Shahar Shani Kadmil, Peter Smets, and our group leader, Leslie Evers, who is a professor at the University of Delft University of Technology, and is the head of the group at KNMI. So, yeah, seismic propagation is probably a topic that you are all very familiar with. So this is kind of an image that I took from the internet, of course, but that you may be familiar with, for example, from your seismological textbooks from university class, where you see either a ray representation or a full wave representation of seismic waves propagating through the different layers of the Earth. But in reality, life is more complex, as we all know. In fact, the solid Earth and the atmosphere couple very well at low frequencies. So the Earth's the crust, as you see here in this picture, is in fact not a reflective layer, as this image may suggest, but in fact a lot of seismic energy is transmitted up into the atmosphere, and that will be the topic of today. The fact that this occurs was already very well known back in the 50s. Researchers in California studied this phenomenon There is, for example, a paper by Hugo Benioff, Maurice Ewing, and Frank Press, who studied sound waves in the atmosphere generated by a small earthquake that occurred in somewhere close to their station in Pasadena in California, and they recorded both seismic waves and infrasound, and that is of course a topic that was further then investigated in subsequent papers. Another say famous paper that studied this in more detail was a series of papers by William Dawn, but also Richard Cook. That is an image of the paper is shown on this slide, and it shows kind of the concept of where you have a propagating seismic wave that propagates along the Earth's surface. In this case, there is a radio wave, and that radiates infrasound locally as the seismic wave passes along. So that's the concept, and not much has changed from that picture. So that's one of the main contributors. So how does it work? Let's get into some of the mathematics. One way to look at it is by looking at the Navier-Stokes equation, which describes the conservation of momentum in a general elastic medium. And you see that here in the upper frame as equation 1. If you expand the variables in an ambient background state and a small perturbation, the small perturbation is then given a subscript A, you can linearize the equation and basically express the Navier-Stokes general equation into a linearized acoustics form, and that's equation number 3, and that basically relates the acoustic pressure with a velocity perturbation VA. Now, what's typically done then is to assume harmonic plane waves, and if you plug that into the linearized order equation, you can basically derive equation number 6 that is shown here on the slide, and this is the basic representation of what the acoustic pressure would relate to in terms of the velocity perturbation and its directivity. So it basically implies that the seismically vertically incident wavefront, which is described by VA inner product with K, is in phase with the pressure, which is described by P head of A, scaled by the impedance Z, and that's rho naught times C. And that is something that if you apply that in real life, you can actually see that it holds. And we'll get to that in the next frame. So what I've shown here is a microbarometer recording, which is with the seismometer recording. Seismometer recording is shown in red. The microbarometer recording, which measures the infrasonic fields, is shown in black. It's bandpass filtered in a frequency band between 0.3 and 0.8 hertz. And you can see that there's if you multiply the ground velocity V, which is measured by the seismometer in red, if you multiply that by a factor of about 400, which is rho naught times C, so 1.2, which is rho naught times C, and take for C 340 meters per second, so 1.2 times 340 is about 400. So if you multiply 400 times the seismic velocity, you get to about an equivalent acoustic pressure, and that's what's shown here. And indeed, you can see for yourself that they're rather well in phase. If you actually look into a broader frequency band from 0.3 to 5 hertz, you see that there is some difference, and that difference can typically be understood in terms of the measurement device itself. So in this case, the infrasound sensor that is used to measure infrasound in the field, and we'll talk more about it throughout this lecture, is a microbarometer that has some sensitivity to the earth shaking itself as well. And particularly this is true for the higher accelerations that are typically measured in the beginning of the seismic wave train. So indeed you see that there's the largest disparity between the red and the black curve, that is in the beginning of the wave train, and that is probably due to the fact that the microbarometer itself also shakes. And for that part of the wave train, that model of rho naught times c times v is not appropriate. But this basically shows you that that indeed the seismic velocity fields and the infrasound fields are related to some extent, and of course we want to understand how and how we can learn from these different conversions. Before we get to some more details, I also want to quote another more historical study. That was a study that came out in the 1980s, so that's about I guess 40 years ago. It was a reanalysis of the 1964 magnitude 9 Great Alaska earthquake. And in this study, Young and Green had discovered that there was in fact anomalous infrasound that was detected all across the United States. So what you would expect from what I showed before in this earlier frame of a radio wave radiating infrasound to right above the atmosphere, there was another contribution from an anomalous region. So what the authors did was they tried to map out where the seismic to acoustic conversion occurred, and they found out that the conversion occurred very clearly along the Rocky Mountains, what you can see here. So you can see here the time of the conversion. So from that paper, it was found out basically that besides a direct path from a seismic wave underneath, there's an additional path from anomalous, where anomalous coupling occurs, and that was identified as being secondary radiation. And we will discuss about this more in this talk. So a big step forward to now. So a lot of the work that is done now on infrasound is done in the context of the Comprehensive Nuclear Test Ban Treaty. That is a treaty that bans all nuclear explosions in all environments, which is in contrast to earlier partial treaties. This treaty has not yet entered into force. So there is a provisional technical secretariat that is basically setting up the network. The network is, well, let me take a step back there. There is a network that is being installed to verify the treaty. That is an international monitoring system. And there is a secretary in place to make sure that this monitoring system is being built and being maintained, of course. So even in this last year of the Corona crisis, the network was very well able to work, and of course we will continue to build on this network in the framework of this treaty. It was negotiated in 1996, in the chairmanship of Jaap Braammakers of the Netherlands. I'm Dutch, so I have to mention that, of course. We did sign and ratify. I believe the United States still does have to ratify, so we're still waiting on that. And perhaps in the next few years that may happen. So the US did sign, but they still need to ratify. The nuclear tests are globally monitored, as I already said, with the international monitoring system, and that consists of various verification technologies, including seismological network, a hydroacoustic network for the verification of the treaty in the oceans, and the seismic network is of course for underground testing, and then the infrasound network is for atmospheric testing, and then there is a radionuclide technology also included, and that's basically to detect any radionuclides that are emitted from any nuclear testing. So it's basically the smoking gun from any nuclear test that can be detected with radionuclide technology. The other waveform technologies can detect an explosion, and that's how the verification system is built. And I do work as part of the Dutch efforts. So I work for the Dutch National Data Center. So the international monitoring system consists of these multiple technologies, as I indicated. So this is a map of all these different sites of the different technologies. So the purple triangles are the infrasound arrays. There will be 60 in total eventually. Around now, there are about 51 built, if I'm correct. So a large part of the network is already in place, so about 90%, and there's still work being done on completing it. So there's a seismic part, as already indicated, a hydroacoustic part. The hydroacoustic part, they actually need very few stations because the ocean is almost acoustically transparent for detection. So with about 11 stations, they can do the job. And of course, the seismic network, which you all know. By the way, the waveforms that I showed previously were from the IS-45 station in southeastern Russia. And there's also a primary seismic station co-located, so that's where I could do the analysis. So some pictures of some of the infrasound sites. This is IS-22 New Caledonia in a rather dense subtropical jungle. This is one of the MB2000 microbarometers that have been produced by France. They're able to measure absolute pressure fluctuations from DC up to 27 Hertz. So it has a very large dynamic range and a very small electronic noise floor. These instruments have been improved over the years, and the electronic noise floor has in fact been reduced. Most of the arrays are 4-element arrays, as you can see here in the upper left. This one has an aperture of about 3 kilometers. The more modern arrays have a larger number of elements because that improves the detectability. And some apertures are a little bit smaller or bigger, depending on how much land they have. But there are basic conditions that the treaty adheres to. And so about 3 kilometers is 2 to 3 kilometers is a typical IMS style arrays, and that's because we want to be able to detect energy in a frequency band between 0.5 to about 4 Hertz, and that's where this aperture is pretty optimal for. But I may get ahead of myself right here. Another one is I-17. This is in Ivory Coast, so a completely different atmosphere. As you can see here, the aperture is a little bit smaller. Again, a 4-element array. You get a lot of lightning detections actually in this area. There are some very nice studies on that part. IS-22 actually has very nice volcanoes in the vicinity that you can do great work with. My colleague and former boss, Alexi, did a lot of work on that. There's Kerguelen, which is an array in the Kerguelen Plateau, which is a very windy area. I'm actually finishing up a study on that together with my colleague and student Olivier den Ouden, and actually a lot of infrasound can be learned from this station as well. So this station itself is very unique in that it has multiple triplets of infrasound sensors, and that's done to be able to improve the detectability because it's so windy. So, and there's another slide here that shows the diversity of the different environments where people have installed the IMS infrasound stations, and basically from pole to pole, we are detecting infrasound on every station. It has its different soundscape, and you want to be able to understand that soundscape to be able to understand also your seismoacoustics that are detected there. See that there's a question. Is there any publications on the lightning detections from the Ivory Coast array? Yes, there are. I will answer it live, I guess. Yes, there are. If you look for Blanc et al. 2014 JGR, you can actually it's about I think it's about both infrasound and gravity waves. Certainly gravity waves, because that's also something that you can detect with these microbarometers. But I will get back to you on that. Type your question again in the chat, and I will give you the link to the reference. But if not, Blanc et al. JGR 2014. So this is a slide that shows the diversity of the different sources that can be detected on IMS infrasound stations. So they include supersonic aircrafts. We measure a lot of those in the Netherlands. Rocket launches, microbaroms, those are basically the counterpart to microseisms. So the continuous background noise from ocean wave interaction. And of course, meteors and earthquakes. And earthquakes is, of course, the topic that we will be discussing today. infrasound from epicenters and ground-coupled waves. I kind of like to enter this topic from about earthquakes and nuclear tests from the perspective of the CTBTO and detecting underground nuclear tests, because the nuclear tests are a very clear type of source. They're an impulsive type of source. So we did quite some research about that. But the research on underground nuclear tests was really also aided by our knowledge on infrasound from earthquakes, because in both cases there are coupled vibrations from an underground source. But in the case of an earthquake, of course, the source is a little bit more complex. So what you can see here on the slides are seismic observations on a station in China at about 370 kilometers distance from the DPRK test site. And it basically shows the seismic waveforms on the vertical components for the 6 most recent tests, ranging from 2006 to 2017. There are some people that claim that in 2010 there was also a test. That one is not included on this slide. But in any case, it shows that the most recent one, and that's the test that we'll be discussing over the next 2 slides, was the largest one. Of course, there is the seismic network that is used worldwide can be used to estimate the seismic epicenter and the magnitude very well as the onset time, so the origin time. Of course, the depth estimates are a little bit more difficult to determine from teleseismic data. People are using depth phases for these, but these may be hard to pick. So one of the reasons to also enter this into this research of seismoacoustics is to see if we could learn anything about the depth of these kinds of events by looking at the acoustics. The yield is typically estimated from empirical magnitude yield relations, and they're strongly dependent on local geology and hypercenter depth. So if you know something more about the depth, then you can also improve your source characteristics. So that's kind of the rationale here. See, there are some questions. Okay, I think I'll get back to that later. How are these waveforms identified as underground tests? Yeah, that's a good question. That's actually the next slide. They actually look like earthquakes sometimes, so it depends a bit. In fact, on this slide, there's a comparison between seismic waveforms from a nuclear test from 2006, which looks quite similar to the later ones, and to earthquakes that occurred in 2017, and people were concerned in 2017 because there was just a test had been done on the 3rd of September, and then there was some more seismic activity on the Korean Peninsula. So people started to look into these other events that occurred, but they look quite differently from the nuclear test in the sense that most of the energy in the case of the nuclear test is contained in the beginning of the waveform, whereas in the case of a seismic or of an earthquake, you can typically see that there's more energy contained in the later part of the waveform. So in this case, between 100 and 120 seconds, you can see here that there's much more energy compared to the nuclear test. It must be said, though, that it also really depends on the local geology. So in some cases, it may be that the larger part of the wave turn is much more pronounced. For example, if your station is located on a sedimentary basin. So it really depends a bit. So, but I think in general, you can say that for a nuclear test, an explosion type of signal, most of your energy is contained in the beginning part of the waveform. Okay, so seismic energy and acoustic energy, and let's take a look at it from a more of a graphical representation to kind of get overview. So if you have an underground source, such as an explosion or for example, an earthquake, there will be seismic body and surface waves, of course, radiating, and we're all familiar with that. But due to the Earth surface shaking, basically the Earth surface kind of moves like a giant speaker, and that creates atmospheric infrasound. And it's quite similar to a loudspeaker itself. The deeper the source, of course, the less the perturbation is on the Earth's surface. And of course, the shaking itself is also dependent on the geology itself. So there are many different parameters to play a role. but in principle, it's the coupling of the vibration towards the atmosphere. So there's a continuation of pressure, but also of vertical velocity, and that basically creates the sound waves in the atmosphere. And there's nothing magical to that. So there's if you apply this knowledge to a typical setting, then you will have infrasound radiating from the epicentral region. We call it epicentral infrasound, and that mostly propagates along its atmospheric path, as you can see here in the upper right figure. There's of course seismic energy that propagates towards an infrasound station and couples locally. People call it local infrasound. So this comes first, this comes last, because it travels much slower. It travels with an average speed of about 340 meters per second, maybe even less. And then there is a third path, which is kind of a mixed path, where part of the energy has propagated as a seismic wave and part has propagated as an acoustic wave. And this has propagation speeds in between seismic arrival times and acoustic arrival times. And we'll see examples of that later. So yeah, as I said already before, characterizing the acoustic energy to determine the source characteristics can be useful because you don't have to have detailed knowledge about the local geology. And this is typical the knowledge that they need to in what they call calibrating the test site. So you really need to know the test site and the geology really well to understand the characteristics of the source. So the idea would be that if you know the propagation paths to the atmosphere, which is also a challenge, you'll be able to tell something about the source, and that's of course interesting. We have to also then know a little bit about the atmosphere itself. So the atmosphere itself determines atmospheric propagation. Temperature and winds are the main influencers of acoustic propagation paths, you can say. The atmosphere itself is a layered medium, just like the Earth itself. The layering is named by the temperature. So the temperature gradients in the atmosphere change from negative to positive depending on the layer where you're in. If you are in the Earth's surface and you go up in the atmosphere, the temperature will drop up to a certain point where we reach the tropopause. That's at about 20 kilometers, a little bit lower, depends on where you are in the world. So you first have this drop in temperature, then you have an increase again. At this point, you have ascended into the stratosphere. Then you reach a point where there's a maximum, that's called the stratopause. And then the temperature dips again into the mesosphere, where you reach the minimum temperature in the atmosphere. And that's about the mesopause, where you enter into space. And at that altitude, you enter into a region called the thermosphere. And there, the temperature does increase, as you can see. Even it becomes higher than the temperature on the ground, but the concept of temperature, of course, in space is a bit different than on ground because you don't have the same kind of density, as you can see here on the right. So the density really drops exponentially with altitude. So it's such a rare piece of air that the temperature has a completely different meaning at that altitude in space. Nonetheless, the temperature determines to a great extent the adiabatic sound speed, and the adiabatic sound speed plus the wind determines the so-called effective sound speed, and that determines the acoustic propagation paths. And I will show you an example next. Something that can be said as well about the atmosphere is that the higher you go, the less well the atmosphere is known. It's basically because it's very hard to measure up high. There have been projects, I could say atmospheric scientists are working on better understanding the mesosphere and the thermosphere, and that also includes infrasound scientists. They want to know better how that part of the atmosphere influences infrasound propagation and the characteristics. Maybe a last word about the wind speeds that occur in the atmosphere, the wind structure. So there's the jet stream that is of course the wind jets that's along which the jets fly. It's typically oriented eastwards. It's bigger during the winter and smaller in the summer. There's the circumpolar vortex, which is the large wind jet around stratopoles. This wind jet changes direction from winter to summer. So during the summertime on the northern hemisphere it's westward, and during the wintertime it's eastward, and vice versa. So this also means that infrasound propagation conditions are dependent on the season. And that's completely different, of course, than in the seismic case, where propagation is always the same. In the seismic case, you just have to compute your propagation conditions once, and that's it. In the case of infrasound, you have to compute it for every atmosphere again, over and over again. And in most of the cases, you don't really get it right. You may get it right to a large extent, but there's always small scale structure that the atmospheric models cannot really represent. So there will always be some kind of difference between your observation and your model. So propagation, the idea is basically refraction. So if you add up the adiabatic sound speeds, which depends on the temperature plus the wind and the direction of propagation, you end up with an effective sound speed. The gradients in the effective sound speed make that your sound will refract, just like a seismic wave in the Earth will refract. So if you have a negative effective sound speed gradient with altitudes, you have upward refraction, and vice versa. If you have a positive effective sound speed gradient with altitudes, you have downward refraction. And because the atmosphere consists of a combination of both, you have these up and downwards refractive paths that are very characteristic for infrasound's long-range infrasound propagation. An example of it is shown here. That shows propagation over the Middle East during the winter time. So during this time, the circumpolar vortex is eastward, as I showed in the previous slides. And in that case, there will be stratospheric propagation due to a waveguide that exists between the ground and about 60 kilometers. And you can see that here in the middle part, there's a acoustic propagation model shown. The darker colors show the acoustic propagation paths. So you have propagation through a stratospheric waveguide, as you can see here. There's a tropospheric waveguide between the ground and about 10 to 15 kilometers altitude. And there's also a thermospheric waveguide. The thermospheric waveguide is always there. It's also a bit absorptive, as you can see here. The energy decays rapidly with range. So the stratospheric waveguide is kind of the long range waveguide that is mostly observed. If you detect infrasound with an infrasound array, you typically observe stratospheric energy, or that's the main waveguide that you're looking at first, or that you're thinking of first, and then you may start thinking about other kinds of propagation conditions, because of course other kinds of waveguides may also exist throughout the atmosphere. If you like to get more involved in this, this is a whole different topic. In fact, so I could talk about this for hours. But if you would like to get your hands dirty with this, I would advise you to look on GitHub for NCPA prop, and you could try to download the package and try to do some simulations yourself, and you could try to simulate these kinds of things as well. And I'd be happy to help you out with that. Let me see, what time is it? 36. Let me move on to the next slide, because I kind of want to get to observations a little bit before it gets too late. So the most recent nuclear test that happened in North Korea was the 3 September 2017 event. It had a magnitude of about 6.1 and an estimated yield of about 200 to 300 kilotons of TNT. It occurred in the Punggye-ri test site below Mount Mantap. That's the test site of the North Koreans. It has a complex geology, and it consists of granite rock. That happens, and after the test, there was a collapse of the underground cavity at about 8 minutes later, and it led to a magnitude 4.1 event. So these events were both detected on the infrasound station IS-45 that I showed before in this talk, which is a 4-element array. It has about a 1.5 kilometer aperture, if I remember correctly. It's at about 400 kilometers distance from the test site, and the back azimuth is about 280 degrees from the north. So that's typically the way how you measure back azimuth. So you consider direction from the north. So 0 is north, 90 is east, etc. So 218 is about south-southwest. And as we will see, is that the bathymetry in the Japan basin, so that's about here, and the sedimentary delta that is about on the border with Russia appears to be important in the analysis of the data. So if you look at the raw waveforms, that's a great way to start, and that's also something we'll do in the Jupyter notebook. You of course take a part of the relevant data. So in this case, you look at one of the array elements. This is element H1. So this is the central element, and you can see multiple. This is bandpass filter between 0.3 and 0.5 hertz, and you see multiple perturbations. And without knowing much about what is going on, you cannot really, of course, tell what is what. So you need to have some kind of inputs out, for example, origin time. Now the origin time comes from the seismic analysis, and that is given as the 0 event time. And based on that, you can then compute what the so-called celerity is, and that basically is the average group speed that a wave takes to reach the station. So 6 kilometers per second corresponds to about a P wave arrival, 3 kilometers per second corresponds to about a Rayleigh wave arrival, etc. And 0.34 is, of course, the sound speed in air. So if there would be a direct acoustic wave in air propagating from the test site, you would expect it to arrive here. And then you see that there are some perturbations arriving with celerities that have about smaller celerities, smaller than 0.34, and that has to do with the fact that infrasound has to propagate up and down. As I've shown you in the previous slides on infrasound propagation, that's typically the case. So you have a longer range propagation. Infrasound doesn't propagate along the Earth's surface, along which you would expect an average speed of about 0.34 kilometers per second, but it has to go up and has to go down. So the path length is much bigger. And because of that, the average group speed is smaller. So the higher the infrasound wave has to go, the lower the celerity becomes. So typically thermospheric celerities have much smaller values than stratospheric celerities, which then again have smaller celerities than tropospheric celerities. So tropospheric arrivals, you typically expect around 0.33 kilometers per second. Stratospheric celerities, you would expect around 0.3 kilometers per second. And thermospheric celerities, you would expect it at around 0.25 kilometers per second. And of course, everything in between is possible. Now, that's what you see here. So there's this 0.3 kilometer per second mark. So that could indicate an onset of stratospheric arrivals. And then there's 0.25 here. So this could be a thermospheric arrival. And so these kinds of marks really can give you a good first insight of what energy is coming in where. And of course, you can then do some further analysis later. So there a further detailed view of the waveform that is indicated by this number 1 is shown here. You see here this oscillating wave train. Number 2 is shown here, and that shows this U waveform, and 3 is also shows this more, it's less well to see, but there's also this U wave shape. Now, certainly for 1 and 2, I can already tell you based on my experience that 2 is typically a thermospheric arrival. And it has to do with the characteristics of the propagation. But of course, that comes with the experience of infrasound propagation modeling. What is really needed, though, is to do array processing, because then you can really tell if the perturbation is coherent, and you can also tell then where what the direction is where the wave is coming from. And that's what is done here. This shows the array processing results, and we will do similar analyses in the Jupyter notebook. So this shows the the best beam. Again, now filtered in 2 different frequency bands between 0.35 and 4 Hertz. So you see it a little bit better than on the previous slide, and between 1 and 3 Hertz. So what is shown here from bottom to top is the frequency content, the best beam. So if you align the traces in towards the direction of the arrival of the waveform, then you get best alignment, and that's where the best beam is found, and it's found for these parameters. So in this case, the wave is best aligned for a direction towards the test site, about 280 meters per second. But you can see that there are some significant deviations from that for the first part of the wave train. And for the second part of the wave train, there's also some energy that seems to align along this theoretical back azimuth that is indicated by this dotted line. So this suggests that indeed this energy comes in from is coming from the test site. The back azimuth, there is some significant back azimuthal scatter, though, and that can be explained by the secondary coupling of acoustic energy from different features, and that is something that we'll get to later. Let's take a little bit closer look at the spectrogram, though. You can see here that the first part of the waveform has about a celerity of about 7 kilometers per second. It has very broadband characteristics, so it has energy content between 0.5 Hertz and about 4 Hertz. But then the later part seems to have much more frequency content around 0.5 Hertz. And that is reflected later by this infrasound arrival, which also has most of its energy contained in that band. This arrival that comes in with about a celerity of about 0.27 kilometers per second has much broader frequency content, though. That, of course, has to be explained. And in this case, it probably is a propagation effect. You can do the same analysis for the higher frequency bands, and then you'll see other arrivals, in fact, also pop up. In fact, the reason why we did this is because they get masked if you do include the lower frequencies. So by omitting the frequencies between 0.35 and 1 Hertz, you actually see additional arrivals coming in with much higher celerities, and these celerities typically correspond to secondary arrivals. So they are refracted somewhere else. They're secondary arrivals, and they correspond to that mixed path of first a seismic wave and then an acoustic wave. That is kind of shown here schematically. So consider a seismic source here, or a nuclear test. The part here is along here has propagated seismically. The part here has propagated acoustically. Of course, the acoustic station observes the back azimuth as if it comes from here. And so using the measured back azimuth, you can tell something at least about the direction of about the radiated infrasound. But if you combine the seismic time and the estimated acoustic propagation time, you can also try to identify the location of the scatterer, and that is something that can be done with the technique called back projection. This is also something that we applied in this study, and the results are shown here. So what is basically done is by combining the information of the travel time and the information of the back azimuth to make these kinds of maps that show where the seismic energy has coupled from the Earth and the sea, in fact, into the atmosphere. This analysis also shows that the radiation of energy is frequency dependent. So to the left, you show the back projections for this more wider frequency range between 0.35 and 4 Hertz. On the right-hand side, the same thing is done, but then for that narrow band analysis between 1 and 3 Hertz. And yeah, you do see that in this case, there is some radiation from the delta area that I indicated previously. And of course, there's the main radiation is coming from the area of the test site itself. Something that was also notable to mention is that there was also some radiation coming from the area that is located actually under sea, and that is a particularity that is due to the fact that is a mechanism called evanescent wave coupling. So in fact, even if a bathymetric ridge is shaking, it can radiate infrasounds that can couple into the atmosphere, and that was observed. Let's see what time it is. 47. How much more do I have to say? So this may be a little bit much. Let's finish up with some other earthquakes where this case of evanescent wave coupling was also observed. So there was another underwater earthquake that occurred in 2004. There was the Macquarie Ridge earthquake, magnitude 8.1 earthquake that was observed at hydroacoustic station and an infrasound station to the south of Australia. So HO1 is on the southwest of Australia. ISO5 is in Tasmania. And in this case, the infrasound station observed a epicentral infrasound, as in the case of North Korean nuclear test. And of course, the seismic arrivals as well, as was presented earlier. But in this case, what was curious is that, of course, the earthquake itself was located under sea. So the case of evanescent wave coupling was shown here earlier as well in this case, and it shows the anomaly that the ocean surface is anomalously transparent for low frequency acoustic energy. And another case that is of interest is to show, and that also shows again these back projections, is a case of where we studied several magnitudes 6 earthquakes that occurred in central Italy in 2016. And in this case, we were able to show for the different earthquakes where the radiation of the acoustic energy occurred using a similar back projection method that as I showed earlier. And it was shown that the radiation occurred from the epicentral site, of course, that is shown here with the star, but also from regions where there's a sedimentary basin, much like in the case of North Korea, and mountainous regions. And that is something that you can then try to combine with acoustic propagation modeling. That is really useful because it also helps to understand where you would expect the coupling that occurs, how to radiate towards the station. Because, of course, there's radiation everywhere, but for an acoustic array to be able to detect it, it also must be able to have that efficient propagation conditions from that coupling to the site, to the acoustic array. So there must be favorable propagation conditions. So yeah, there's a lot of information I think to cover. I think we can perhaps discuss a little bit more live. That may be helpful as well. I think overall, in conclusion, what is to say is that earthquakes and underground nuclear tests give rise to seismic and low frequency acoustic signals or infrasounds. These kinds of signals can be detected with array processing techniques, and we will play a little bit more with that in the practical session. Back projection will allow you also to visualize the locations where the seismic energy is radiated into the atmosphere, and for that energy to be able to detect it at the station, you also need to understand the atmospheric propagation paths. So seismoacoustic analysis really goes hand in hand with atmospheric propagation modeling. These conditions change also seasonally, so that also has to be considered. So if you have, for example, an earthquake that occurs in the winter and an earthquake that occurs in the summer close to an infrasonic array, the observation may change dramatically. And lastly, I think what is an interesting take of these kinds of seismoacoustic analysis is that it's useful to characterize underground events such as earthquakes and nuclear tests without having detailed knowledge of the local geology. And so with that, I would like to stop this talk and perhaps discuss a little bit more and also go through the Jupyter notebook.
Awesome. Thanks so much, Jelle. That was great. I think let's maybe pause just a minute or two and see if we have any questions about the end of the lecture. And then do you want to take a couple-minute break before we move into the notebook? Okay, it looks like maybe we don't have any questions. So yeah, I think we could move into the notebook.
Okay. And maybe, oh, sorry, you're muted? No, I'm not muted. Great. Okay.
Oh, perfect.
Do you see my screen?
Yes.
Okay. Yeah, maybe the questions will come along the way, and that's also cool.
That,
so.
Yes, I believe everything. It looks great to me.
Okay. So there was of course a lot of stuff, a lot of ground to cover. I think what I wanted to do was to give you kind of a flavor of what is in there for seismoacoustics, but it involves a lot of different disciplines. So in this lab, I just wanted to treat really the basic signal processing things that are useful to do when you are trying to analyze an event. So for this reason, I prepared a notebook for your analysis. I think it's very useful because you can interface directly with different APIs that are out there, the different FP7 Web Services and such, to be able to download event data, the parameters, but of course also download the data itself, download the metadata, and then using that do basic analysis, look at the array response, do some basic spectrogram analysis, kind of similar to the plots that I've showed you during the lecture. And then at the end of the lecture, at the end of the lab, there will be, of course, some beamforming and some detailed FK domain analyses. And there are some additional bonus exercises that if you feel inspired to do it, you are invited to do so. But let's get started first. So first, I always load these kinds of comments so that I can plot my plots with matplotlib and everything. Load NumPy. So the first thing that I do is, for example, load an event. And I make use of the FP7 Web Services that are part of OpSpy. So they're well known. I believe you have already gotten a lecture with from OpSpy, so it must be quite easy. So what I do here is that I make use of the USGS catalog. So what you can do is, what I typically do is whenever there's a seismic event that is of interest, I take a look, for example, significant wave earthquakes archive, for example. I take a look at the event page. And then at the origin tab, I look at the at a particular ID, of course, that is associated with this earthquake, and then you can fill this in your the form here. So in this case, we're going to be downloading a earthquake from the 24th of August 2016, which had this ID. And if we do so, we get the parameters of the earthquake itself, according to the USGS. Hopefully it's pretty fast. Yeah, indeed. Well, this is when the event happened. Indeed, the 24th of August, 36 past 1 about, and it occurred in Italy. And you can of course plot it. So for example, the orthographic plot or the local plot, whatever you like. Sometimes it takes a little while. While that is loading, we're going to be working on loading some other OpSpy. We'll run through some other OpSpy functions. So what we're going to be using is the array processing routines later on. GPS to this azimuth is another. Here's the map of Italy, by the way. It's quite zoomed in, so it's actually less easy to see. So let me just keep the ortho map. So the OpSpy routines are loaded indeed. So the GPS to dist azimuth is a quite useful routine to compute the distance in the azimuth between two latitudes and longitude points. Of course, the read routines are a must to load UTC daytime. So that's loaded. I made some wrapper functions. They're homemade. They're, I think, quite useful to get data, write streams to an SDS data structure. That's the type of structure that I typically put my data in. So what I typically do is that I download the data first. I store it somewhere in a local file. So for metadata, this will be station XML. For waveform data, will be minisheet volumes in SDS archives. And then later I can read them in again. So you don't have to keep downloading them over and over again. So yeah, these are the fields that describe the station that we're going to be using. So this is station IS-26. It is a station that is part of the IMS network, but it's also part of the German national network, of which the network code is GR. Let's take a look at the verification network again. So this is the website of the CTBTO. So again, this is the monitoring system. So all the different monitoring techniques. These are the infrasound stations that are have been installed for or are being installed for the verification of the CTBTO. In fact, some of these are publicly available, not all of them, but the station in Germany is IS-26. So what I also like to take a look at typically is the Iris web service. That is this link, and if you click on it, you see all the publicly available CTBT stations. They're basically the stations that are part of the US efforts. So while the US hasn't ratified, they do provide public access to the network, so that's very nice. The Germans have their own network codes, so that's GR. I should have added it here. So you see GR as well. These stations are part of the British network, and then the Australians also have public access to their network. And then, of course, the Germans have access to their to their infrasound stations as well. So this is the station that is which is what we're going to be using. That is that's the first infrasound station that was certified IS-26 on the border with the Czech Republic and Germany, in the town of Freien, close to Austria as well. And we're going to be analyzing the the earthquake that occurred in Italy. Let me also for fun the network that is part of the Dutch network, and that's the network that I'm responsible for. So that's in purple here. So we have several arrays in the Netherlands. This is actually my hometown, where I'm currently talking to you from. So this is one of our infrasound arrays close to our institute. It's really loading the map. Here it is. So this is my institute, KNMI. This is the array in the backyard. You can see here. Oh. So you see here, in fact, different stations. But this web service is very useful, I find. Let's get back to the notebook. So let's load the parameters for the IS-26 station, or I-26DE. That's the other name to be able to download the data. I typically set these parameters to set the names for the metadata and the SDS routes. So that's the data routes for where we're going to be storing the data later. I make use of the what is it called again? The Iris Federator. So there's a new kind of router that is able to route through all the different data centers. So as you see here on the Iris website, there's many different data centers that you can query for data. So I used to actually look at the individual data centers, but they put a new tool in OpsPy so that you can query them all at the same time. And that's very useful. So that's what I do here. And then I make some pointers here to where I'm going to be finding the local data and the remote data. So first I download the inventory with this get metadata function. So that's that homemade function that I gave you. I queried from a remote web service. So this Iris Federator with these different parameters for the network, station, and the channel. So and indeed, then it downloads the metadata for the IS-26 array. So that's something probably that you're familiar with from other ROSES modules. Given this inventory, you can compute the distance, of course, to the event. So that is something that you can compute with this GPS to dist azimuth function. And then you can print things like the distance from the first element, which is typically considered as the reference element. You can compute the source receiver azimuth. So that's the azimuth along which the propagation occurs. And also the back azimuth. So that's the back azimuth that you would expect IS-26 to observe if propagation would go along a straight line. Then the waveform data, you can download that too. For that, it's useful to determine the two start time and end time, which I have denoted here by T0 and T1. T0 is the origin time minus 60 seconds, just for safety. The T1 is given as the distance between the source and the receiver divided by the minimum celerity. Let's see if there's a question. How are these waveforms identified? Oh, sorry, there's a new question, I think. There's an open question, yeah. Is it possible to compute the back azimuth if the event origin location is unknown? No, that's hard. You have to know at least, you have to at least know the area of where it's coming from. So the back azimuth is really, the nice thing about this kind of seismoacoustic analysis is that you know something about the epicenter that is provided by the seismic network. And with that information, you have basically the origin time, and you have the back azimuth. That's information that is needed. Because the origin time is also part of this, as you can see here. It's shown here. So what I do here is divide by minimum celerity, and the celerity is something that I introduced in the talk. So again, it's the average group speed that it takes an infrasonic wave to propagate from source to receiver. So I take about 0.15 kilometers per second. That's very slow for an infrasonic wave, but then with that, you are at least sure that you have most of the data that you need. So I could probably also go for 0.21 because that's typically the lower end of the celerity range for the atmosphere, for Earth's atmosphere. But I just take a little bit extra here for safekeeping. So with that, I download the data. So similar as with the metadata, I do it now for the waveform data. It takes a little bit longer. So I also take a little bit of a margin. I typically take 10 seconds extra, and then I cut it off later because sometimes in some cases of FP7 Web Services, you don't get exactly the data between the T0 and the T1 that you want. So then I I request a little bit extra and then I trim it again later. And then you have the data in your stream between 135 and 252, and that's exactly what I wanted as well. The data sample is sampled at 20 Hertz, so you can reconstruct the field up to 10 Hertz. There are 8 elements of the array, and we'll take a look at the array itself after storing the data with the stream to SDS function. So with that, I store the data into this SDS data structure, and that is a very useful structure to later query the data again using the SDS client that is also part of Spine. Okay, then we get to the processing of the data. We can read the inventory with the standard function. Then we have the inventory again. So basically, this assumes that you can just start here. Say you have downloaded the data and you want to reanalyze the data again. You can just start here. Just start from read inventory. Of course, you have to make sure that you have loaded the functions itself, but you don't have to then download the data again. With the inventory, you can plot, of course, the array layout, and that's shown in that plot that is coming up here. So indeed, there's 8 elements. In fact, it used to be a 5-element array, but they added 3 extra elements, and that's really included. That increased their detection capability of the array. So it's about a 1 or 2 kilometer aperture array. I don't quite remember. I believe about 2 kilometers. You can also take a look at the response of the array elements. These are MB2005 elements, MB3 elements. Apologies. So the response of the microbroms are shown here below. There's an amplitude as function of amplitude response and phase response as function of frequency. So you see that there's a corner frequency at about a little bit below 0.1 hertz. I would say at around 0.2 hertz or something. But because you know the array response, you could deconvolve with the array response and also consider very low frequencies. Something good to mention also with this kind of station is that in fact also measures the absolute pressure. So there's 2 different channels, the BDA channel and the BDF channel. The BDF channel is the filtered channel, and the BDA channel is the unfiltered channel, and that has much larger pressures. Of course, that is like hectopascal pressures, and here we're interested in millipascal pressure. So the difference is the dynamic range, but that's a detail. Here's again that same function that same cell that was done previously. It's just in case you start from this part again, then you need it. And the computation of T0 and T1, that's also the same. So here you just reload the data again. So of course this is a bit foolish because we just downloaded the data and it's still in memory, but you understand what I'm getting at. So this is the raw data in counts. So this is typically what you get out of the waveforms or out of the FP7 Web Services. So it's impossible to see what's going on here. This is the pressure or filtered pressure data in counts, but you cannot see any coherent infrasounds. And for that, you need to filter first. So what we do is we'll apply a deconvolution filter. We deconvolve with the instrument response because we have it. So I do that with corner frequencies between 0.1 and 9 hertz, and that's appropriate for this response function. If I do so, I can plot it again, and then you will see the results now not in digital counts, but you actually see it in Pascal, and you see that it's measuring. There are some coherencies that you can see here in the first part and in the second part of the wave train. And the peak-to-peak amplitude is about 0.1 Pascal. So that's very small. So that's, if you I think it's about a centimeter distance. If you move your finger up and down a centimeter, that is about that distance, or that corresponds to that pressure difference. So it's a very small pressure difference. You can do spectral analysis. This kind of standard. So typically, I take the first element of the array. Well, then I do a standard SciPy kind of spectrogram. You'll be familiar with that. I guess what is noteworthy to mention is that typically the spectrogram output is well, you can scale it, of course, in different ways. You can plot the spectral density. You can also plot the spectrum itself. Scaling is a little different. You can plot it in terms of a dB value, and then typically a reference pressure of 20 micropascal is used. And that corresponds to the audible range, audibility threshold. So for infrasound, it's a bit useless in a way, but it's a kind of convention for acoustics to do. This is kind of a cell to define celerity tick marks. So it's kind of a useful cell for later. And then this cell will give you this waveform plot together with the spectrogram. And then the celerities are plotted here above. You see that the 7 and the 3 are kind of on top of each other. That's a pity. But why I've taken 3 is because it is the appropriate propagation speed for a Rayleigh wave, and that's indeed when you see a Rayleigh wave coming in. You may also see some dispersion even. Arriving there. And then, of course, around 220, there's another bit of coherent energy coming in, and that corresponds to the acoustic arrival with a celerity between 0.3 kilometers per second and about 250 meters per second, or 0.25 kilometers per second. With this, I typically make my mind up in terms of what kind of frequency range do I want to take for my beamforming analysis, because what you see besides the transient energy, which has energy below 0.3 hertz, is that there's also a whole lot of coherent energy that is likely to be coming from microbaryons. So microbaryons are these basically the infrasonic counterpart to microseisms. So what I typically do in this case is that I filter out the microbaryon. So I take a minimum frequency of about 0.3 hertz. In this case, a maximum frequency of 3 hertz to filter out local infrasound that is not that's probably not relevant to this event. So this is the bandpass filter that is very straightforward, standard infrasound standard OPSPI stuff. Sorry. And after filtering, you get something like this, where you see this first arrival, so the seismic arrival, the infrasonic arrival, and if you look kind of closely, you see also some coherent energy in between. And that's we're going to be looking at a little bit later after doing array processing. That's where we're getting at now. So array processing itself, I can guide you to the ROSES 2020 module that was taught by Professor Stephen Aerosmith, who is at SMU Dallas, Texas. So he has a very nice overview of the different methods and also network processing methods that I can recommend you look at. It basically will give you a background in how array processing works. And but what it basically does is that you try to identify the direction of the wavefront by looking at the travel time differences between the different array elements. And because array element 2 in this case detects the wave first, then element 1 and then element 3, you can figure out that the wavefront comes from the southwest, and that's basically the sun that is the thing that is being calculated in an array processing routine. Well, we will work here with the array analysis modules that are implemented in OPSPI. They work quite well. There are good examples of typical FK processing routines that are the workhorse algorithms for many studies. You can find many different routines online. I have developed several myself as well. Mine are in Fortran that are somewhat optimized because they're fast Fortran compilers. Also, I have different ways how you can define the slowness grid. We'll get to the slowness grid a little bit later. Yeah, they're there. You can take a look at them if you're interested, and perhaps try them out. And there's even further optimized routines of these algorithms in a combined Python Fortran language, and they have been developed by the team of people that have been that I work with, and we will probably publish these in the near future. Something that is also nice to mention is that there's also high resolution methods, such as clean beamforming. I could guide you to a study by Olivier and Auden et al. It's a student of mine who published on this in 2020. And these kind of methods are very useful if you want to detect multiple infrasonic sources within one time window. But we're not going to get into that here. First, we're going to evaluate the array response. That's the we're going to do first. What we're going to do is load the appropriate functions. It's also built in OpSpy. So what you're doing when you want to compute an array response is basically to understand what answer you get back from an array if you give an array a monochromatic wave with a certain frequency in a certain direction. So the typical direction that you give that wave is a vertically incident wave. So it either comes in vertically incident from below or from above. It doesn't really matter. Because of that, k naught equals 0 seconds per kilometer. And then you find the maximum of the response at that value. But you will also find side lobes, and we will see that in the following example. The reason for that is that because you don't sample the wave fields everywhere, but it's only at discrete spots, you get something that is called spatial aliasing. And that spatial aliasing is found for the reason because you don't have elements everywhere, so you can only recover wavelengths that have the distance of your sensor distance. So that will be shown in the following example. So what we're first going to be doing before plotting the response is to add the information of the latitude and longitude from the inventory to the stream itself, and that's necessary for later. Also, I'm going to be storing it in this this new NumPy array and this quartz NumPy array. And this quartz NumPy array is needed to be able to compute the transfer function. So when I compute the transfer function, it evaluates that this integral over here, in fact. So what it is that you sum these monochromatic waves as if they would come on different array elements, and then you divide by the number of elements. And so this gives you the narrowband response. And if you then integrate over frequency, then you get a broadband response. So if you would look into the guts of this function of OpSpy, then you would basically see this happening. And of course, you can reassure yourself that you find the maximum back for k equals k naught, because in that case, this disappears. This becomes 0, and you basically start adding up ones. And so the response is then 1 for the position k is k naught. So in the case of a broadband response, it's you don't typically express it in terms of wave number k, but in terms of slowness s. and slowness and wave number are related to the frequency as shown here. Okay, so we have computed now the array response. So officially it's called the Bartlett array response. That's just the way how the Bartlett beam is defined. And if you plot it, then you get the following. So this is the array layout again. So indeed about an aperture of about 1.5 kilometers. And to the right, you see the response function itself. It's normalized. So in this case, indeed, you do find the maximum of the response in the center for the slowness, the x slowness and the y slowness being 0. And this is also the thing that we gave to the array response. So it will be strange if we didn't find this maximum back at as a 0. But let's see what happens if you change the limits. So in this case, we have defined the limits to be the minimum and the maximum of the processing bands. But if you change this, for example, to for example, 0.1 to 0.3, leave it like this. We plot it again. You see that the Bartlett response looks completely different. And if you make it even more narrow, if you start at 0.2 and you end at 0.21 or something, and you do a step size of 0.01, you start that there's all kinds of side lobes that start to appear. So this is due to the fact of spatial aliasing, and it makes the FK analysis becomes more difficult because there may be additional maxima that you have to take care of. If you look at higher frequencies, it becomes even more pronounced. For example, here. And then you can see indeed that there are these multiple side lobes, and they may confuse you in your FK analysis. Okay, that's not the case. We have a nice response in the frequency band of our interest from 0.3 hertz up to 3 hertz, and we take steps of 0.3 hertz, and that's you can of course change that as well. Okay, now let's get to the actual beamforming. So there's this the processing routine. There are several parameters that you can also change. You can change the window length, the overlapping parameter. That's called WinFrac in SPI. Here we're going to set it for 0.5 now that it's 50% overlap. But you can also change it to, for example, 0.1 for 90% overlap. Or vice versa, 10% overlap would be 0.9. Let's do 0.5 for now. The window length is 20 seconds. The slowness stepping range is the, well, I didn't explain it yet. That's defined as the stepping of the slowness grid. So to do so, of course, we first have to define a slowness grid. So slowness grid is, of course, the slowness is the parameter of your wavefront. So you have to define the grid over which you do the beamforming. So in this case, we define it to be a maximum of 250 meters per second. And we have to express it in seconds per kilometer. So this is the reason why it's multiplied again by 1,000. So this defines the upper limit. So basically, on the edges of the slowness grid, you would expect waves to align with speeds of about with speeds of 250 meters per second. So if you go further inwards in the slowness grid, you get at some point to this green ring, and that's about 340 meters per second. So that's where you would expect atmospheric energy to align on. And then there is an orange ring, and that's 3 kilometers per second. That's the Rayleigh ring, and then there's the P wave ring. So that's all the way in the middle. So you can also see that it can be in fact much harder with this kind of array to to characterize seismic energy, because it is a much smaller array, and you would expect perhaps a little bit bigger array for for a seismic array. That's in fact also what the co-located seismic array, the GRS array, is, of which the IS-26 array is only part of. So the different arrays also have different characteristics, and that's what you see here. But we're mostly interested here in the characterization of infrasound. And as we will see, the characterization of the seismic energy also goes fairly well. But ideally, you would like to have a little bit of a bigger array for seismic energy. So then we run this. So the stepping size is, of course, obvious. That basically divides up the grid size of the slowness grid. So I take here 25 steps, both for the X and the Y direction. So the slowness limits are given here in the upper row. The window length, the window fraction. The frequency range is the frequency range that you've already seen. So between 0.3 and 3 hertz. And then there's a start time and end time that have been given. And then we can start the array processing itself. So that takes a little bit. And of course, if you change this window fraction to, for example, 0.1, it will take longer. If you change the window length to bigger or smaller scale, it will take longer or less. But this is about a good parameters for this event of interest. Okay, now we have an output that is saved in this out array. So this outputs time semblance, and they call it relative power, FK power, and they call it absolute power in the OpSpy manual. And then there's back azimuth in degrees relative to the north, and slowness in seconds per kilometer. And typically like to rearrange some of these parameters a little bit because it's for infrasound plots, it's typically nicer to look at meters per second for apparent velocity. That's something else. Oh yeah, and another thing that I do like to compute, and that's given the semblance parameter, is the Fisher ratio, and that is something that I will show next. But the Fisher ratio relates to the semblance as this, and you can look at Stephen Arrowsmith's notes for a description on that. The Fisher ratio is a useful statistic, and it has some desirable properties, and therefore it's useful for detection. Under the assumption of Gaussian white noise, it's unity. So basically you can tell if there's a deviation from unity that there is something going on, there is a bias. And typically you may expect that there's a signal. So this is the reason why I compute it and why I like to plot it with the array processing results. Using because of these statistical properties, you can also associate a probability of false alarm with it, and this is of course useful, certainly in the case of low signal-to-noise ratios. Okay, well, with that then we get to one of the final figures, and that's plotting of the beamforming results. So this kind of collects all the different parts that we've been doing. So it will plot the spectrogram, the waveform, the back azimuth values, the apparent velocities. I actually will divide it up into different parts because you have a very large dynamic range of apparent velocities because you have seismic velocities and atmospheric velocities. And then there's the Fisher ratio that I will plot and the FK power that I would like to plot. And that's it. And that's the results. So what I also plot is some information about the event itself, so where it was, the magnitude itself. So this comes from the event FP7 Web Services, of course. I give some information about the distance to the array, the name of the array, the theoretical back azimuth that is also shown here by the dotted line. And then I show here the spectrogram, the best beam, or in fact, this is not the best beam. Apologies, this is just the first element. But it's well, it does show, of course, the waveform itself. Then the back azimuth, so that corresponds to the direction of arrival of the waves, the apparent velocities, and then the Fisher ratio as a function of time. And in blue is shown the Fisher ratio, and in red is shown the FK power. So the FK power is the basically the sum of the power on the traces, and that Fisher ratio is the derived statistic. And now you can also see why it's such a useful statistic, is because you can already see that even before the FK power starts to increase dramatically, you can see that the in fact at the onset of the P wave, that the Fisher ratio starts to deviate from unity. So this is one of the good reasons to use the Fisher statistics. You see that the array on the back azimuth and the apparent velocity, you see that the different arrivals align with along the back azimuth of expectation for the local infrasound and the epicentral infrasound here, that are characterized by the celerities as the epicentral infrasound at around 0.28 kilometers per second. The local infrasound is arriving with about 3 kilometers per second, and then there's also some intermediate infrasounds, some secondary infrasounds with back azimuths that deviate from the theoretical back azimuth, and they appear to come from a different region, for example, due to topography or the sedimentary basins. What is also nice to do is to have a look at the FK analysis plots, and that's the last part before we get to the exercises. So for that, it's, for example, nice to so it's basically these kinds of slowness plots that kind of give you an idea of along which slowness the energy is aligned, because in this kind of plot you only see the maximum as a function of time. But it's, for example, nice to for this time frame between 2:15 and 2:20 to take a look at the slowness plot. So I included a function for it as well that is adapted from a function that Stephen Arrowsmith coded up for last year's ROSES. So you can, if you like, further modify it as well. But what it does is that it shows the FK plot, the FK power, the semblance, and the Fisher ratio. In this case, for the time window between 2:15 and 2:20. And you see in this case, indeed, that the Fisher ratio has much reduced side lobes when compared to the FK power and the semblance. So this is the reason to look at the Fisher ratio when it comes to these kinds of plots. Okay, well, this kind of concludes kind of the type of analysis, the kind of array analysis that you can do very easily with FP7 Web Services these days. So in fact, you could easily just change the events of interest. For example, you could you say, well, I'm actually interested in this very recent Alaska earthquake. Just do that. I change the event ID to that event of interest. You take a look at it. It's indeed that event close to Alaska. And then you change the perhaps some of the parameters. You can say, well, I'll take a look at station ICE 53, which is in Alaska. Of course, you would have to check this with the IRIS website. And of course, you can see then here that that is a station in Alaska that may be worthwhile checking out, ICE 53. So you change these parameters. It's the same story again, but now for ICE 53. So you see that these parameters change immediately as well. The time frame, of course. So it's very easy to do this without having to change many different parameters. It all can be calculated on the fly. And the waveforms, I hope they won't take too long in this case. Yeah, there they are. Also 8 elements, 20 Hertz, same story. We save them again in a different Different directory than IS-26, of course. You can plot the response, the array layout. It's a little bit different, as you can see, than IS-26. The characteristics of the instrumentation is a little bit different as well. It's a different instrument. You see that the roll-off is a little bit different compared to the station, the sensors for IS-26. Yeah, and then you can plot the data as well. So you can see here that there's a fairly large, in this case, seismic arrival or local infrasound arrival, plus some stuff coming after, but there doesn't seem to be a very strong epicentral infrasound. So we can take a closer look with the array processing to see if that's indeed the case. And then, of course, you can ask yourself the question why that is. So you can see that there's a very long tail that seems to be coherent, so that's maybe interesting. It often has to do with the response of some local mountains close to the array itself that start to radiate. Okay, so we computed the spectrogram, plot the spectrogram. Here you see that there's indeed also again, of course, strong band of microbaryon energy. So let's take the same band, maybe a little bit higher, 0.5 to perhaps 3 hertz. Just to get rid of the microbaryons as much as possible. Plot the array response again. That's a very narrow lobe, so it should be even more precise than IS-26. Probably has a little bit larger aperture, so that corresponds to the different behavior of the response in this case. And then you can do the beamforming again, as we did for IS-26 with the Italian earthquake. Take a few seconds. Another good reference, by the way, to look at is the PhD thesis by Professor Jelle Assink. So he wrote a lot about the signal detection using Fisher statistics. So if you're interested about the desirable statistical properties of the Fisher ratio, be sure to take a look at that. Okay, plot the analysis results. And in this case, you see indeed again the seismic arrival coming in with the expected celerity of about 3 kilometers per second. And you do see some coherent energy coming in with about 0.5 kilometers per second. So it's not very clear in the spectrogram, but it's certainly there. It comes in with atmospheric propagation speed. So that this kind of combination of lower celerities than seismic and atmospheric apparent velocities are typically a clue that it's secondary infrasound. And so it's completely different than the Italian case. And of course, you can also do an analysis again. Take a look, for example, at the time window between, say, 6:55 and 7:05. Let's just put this there. Uh, 2021, 7:29, 6:55. Okay. Now you see here the peak, the peaks, of course, this time frame. So you, in fact, also see all these different side lobes. But the energy appears to arrive coming in from the west. Okay, so those are a few examples, but there's many more examples, of course, that you can do. I've written a few bonus exercises that you can try to carry out. You could, for example, take a look at the other magnitude 6 earthquakes that happened in 2016 in central Italy. There were 3 that occurred in the fall, 1 in August and 2 in October. So that's, for example, interesting to look at, also to understand the influence of the atmosphere. Google Earth is a good, useful tool to try to understand where the secondary arrival appeared to be coming from, and then it's useful to look, for example, at mountains or sedimentary basins. You could also look at an earthquake and try to include many different arrays and see how the different arrays observed that earthquake, because every different array has its own view of the earthquake, also due to the different propagation conditions. And again, you can make use of the map service of IRIS and a seismic catalog of your preference to get information about the idea of this particular earthquake. You may have to change the frequency bands depending on the array that you consider. And yeah, it could be interesting to map out, because you have multiple arrays to map out where the energy appears to be coming from. You may be able to detect the epicenter infrasound on all the different arrays, but the secondary infrasound may only be appearing on one of the arrays or 2 of the arrays. And of course, there's also more exercise that you can do. For example, you can take a look at one array and look at many different earthquakes that have occurred in the vicinity of that array. For example, look at different intensities or different depths and take a look at what the characteristics of that earthquake was. It could be a very good starting point to do that. And for example, IS-53 could be a nice array to start looking at that. And yeah, if you feel really excited about this, you could even try to back project these kinds of array processing results yourself. And a recipe for an algorithm can be found in this study that studied the 2016 Central Italy earthquakes. So if you go to section 3, there's basically an algorithm that explains how these kinds of maps are made, and you can try to replicate these maps yourself. So if you feel like it's, yeah, I'd be very interested to see if you are able to do so. And if you have any questions, I'd be happy to answer them. Thank you.
Great, thanks so much. I think we will wrap up for today, but yeah, please try your hand at all of the exercises, particularly the bonus exercises, and we will be excited to see your results. And thank you so much for the lecture and the overview.
Cool, thanks.
Okay.
Yeah, I'm looking forward to it.
Okay, great, thanks.